G'day everybody, this is my talk MySQL and InnoDB for the rest of us. It's my attempt at democratizing some of the very basic knowledge you need to run performant queries on MySQL. My name is Shaun O'Keefe. I'm Head of Platform Engineering at Style Education. This is us. There's about 50 of us. We're a small company that makes an e-learning platform, which is a blended learning platform, which is basically a tool which is meant to be used by teachers with their students in class. We're not set and forget homework. We're a tool that's meant to augment learning and make it a lot more exciting for kids in STEM. This is my Twitter handle. I would encourage you not to actually follow me. Let's talk about what we're going to talk about. First of all, we're going to be talking about MySQL. I'm guessing that's the reason anyone who's here is here. We're also going to be talking about InnoDB. We're going to get into a bit more about what this is later on, but very specifically, we're going to be talking about performance. So, quick question, just ask around the room. Who knows why this query is slow? Anybody? And why would this one be slow? Any takers? Where's all my disk going when I'm creating a table like this and running a query like this? The goal of this talk is that basically by the end we're going to be able to answer these basic questions with a few very simple tools and a few little bits and bobs of knowledge. So let's get into it. MySQL, we all probably know what this is. It's one of the two databases. It's the dolphin one, not the elephant one. This talk isn't really championing any one or the other. This is just the one that I've had the most experience with. An important thing to talk about when we talk about MySQL is InnoDB. What's InnoDB? InnoDB is InnoDB. InnoDB is one of MySQL's storage engines. Storage engines are a big sort of feature of the MySQL ecosystem. The Spruit is a great way to get a bit of flexibility into it. Their basic purpose is to run all the parts of disk I/O, manage indexes, do all the parts that are like actually interacting with records so that MySQL can do all the smarts around planning and thinking about your query. The structure of the server is something like this. We have an ongoing competition to see who can make the worst hand-drawn diagrams at Style, and guys, it's not even close. I am the all-time champ. Our server basically contains a number of things. First of all, it's the interface to the SQL language. It contains a query parser, which will tokenize your queries and put them into something which the server itself can interact with. It has a query optimizer. This will refactor, move around parts of your query, refactor the token tree of it, so that it's going to run a lot better. It will make a number of clever decisions based on asking questions to the storage engine around the cardinality of rows in certain tables or what indexes are available, and it will actually rejig your query to use them efficiently, and it will make decisions about what indexes it's going to use. It's also responsible for handling client connections. Now, what does the actual storage engine do? Storage engine handles, first of all, obviously storage. It's responsible for writing rows to the disk and reading rows from disk efficiently. Accordingly, it also manages indexes, which are a way to get quick access to stuff either on disk or in memory. And it manages a few other important things like the buffer pool, which you'll often hear about when you read the MySQL docs. This is mainly around just caching things like our actual tables or our indexes to get fast access in from memory. It also exposes an API to ask questions, as we said before, about what data is in tables, what it looks like, its cardinality, how fast we can access things, and a whole bunch of other stuff too, which we don't need to cover for this talk. Now, as I said before, storage engines are pluggable. There's a whole bunch of them available. You can all breathe a sigh of relief. I'm going to absolve you from the need to understand what these are. Basically, if you don't know which one of these you need, then you want InnoDB. When you need one of these, I promise you'll know. So let's talk about performance. There are three fundamental things you need to think about performance when you're talking about SQL queries, and those are query time, and query time. Basically, this is your contract with your user. This is what your consumer cares about. They are sort of like, the game is basically that you want to say, that little number that pops up at the end of a query, the number of seconds that it takes, you want to minimize the average, or maybe like a percentile number of that for the sort of all the cases across use cases of a particular query. Now, with the same sort of adage that I've lifted this from, the location one from real estate, like that obviously has the sort of caveat that you want to think about location, and also about like catastrophic market corrections, which will plunge your economy into the doldrums for 10 years. For the same reasons you wanted with databases, you want to think about query time, query time, query time, and memory and disk. Obviously, if you have problems with either of those, you're going to have trouble. But the bottom line is basically what you really are optimizing is query time. We're keeping an eye on memory and disk though. So how's this relationship work? I think as engineers, we want to kind of have one of these nice triangle things where we do a choose to and say you can have memory and disk but not query time or some other combination. In actual fact, this isn't really how it works. The relationship's a bit more inscrutable. It looks a bit more like this. And basically, you actually are going to see the case where query time, memory and disk are actually sort of like correlated. Like if you have a high query time, you're probably going to be using lots of memory and disk. And in fact, making your queries faster are going to reduce the amount of memory and disk you use. So an example here is a bad index. A poorly designed index is going to use lots of disk. It's going to be slower to move parts of it on and off disk or into memory. Accordingly, it's going to have a longer query time. And it's potentially going to be very sparse and use up a lot of space and require you to use more memory. Conversely, so not conversely, but also like, for example, if you have a query that is using has to use temp tables to do sorts, that's going to use a ton of memory to actually pull the data out of disk and then do an in-memory sort in the server. If that memory gets too large, it'll be paged out to disk, which uses up, again, more disk resources. And that is actually one of the slower ways to run a query. Avoiding that memory usage will actually make your query faster. So it's actually really just something we want to kind of optimize all these three together. So if we're talking about query time, what takes time in queries? Fun fact, this list of bullet points is also kind of directly maps to all of the different states that if you run show full process list in your server, all the different states a thread can be in, each of those probably correspond to one of these. So let's run through them. Your server can be basically planning how to run a query. It can be looking at your SQL, breaking it up, and then thinking about how it should do it. It'll be making questions about statistics to the storage engine to figure that out. It may be executing a query. Once it's made a plan, it will go through the process of then making queries out to the storage engine, finding rows as we've got listed there as well. It may be stuck on a lock, and that could be a table lock. It could be a row lock contention, which is somewhat minimized in MySQL, but still ever present. It could be moving data between memory and disk. If we run a large query that needs to be sorted, whose results need to be sorted or post-processed by the server, it may need to be moving those out to disk to actually be able to handle the size of it. It may be sorting and grouping results using that table manually in the actual server. And this one's not to be overlooked. It may be sending the data across the wire back to the client. Sounds boring, is actually a really important part. Again, as engineers, we want all of our queries to be having problems with things like locks and fun things where we get to use our sort of CS degrees to figure them out. In actual fact, the vast majority of queries are going to be having problems with two very boring things. First of all, are you fetching too much data? And this one's really simple. If you have a big star next to your select, you're probably fetching too much data. This causes a number of problems. One, if you are not actually using all of those columns, you are doing extra work to get all those values off disk. And worse, you're actually sending all those values across the wire back to clients. It sounds really boring, but if you remove that star and put in the specific columns you need, you're going to remove a ton of the work that your database is doing. Now, the second one, if we get rid of that first one, the second one is a bit harder to fix, and it's a bit more nuanced. This is, are you looking at too much data? Basically, for every row that you return to the user, how many rows do you need to inspect in the database? Is it 1-to-1? Is it 100 rows for every one that you return? Is it 10,000 for every row you return? Now, the reasons why we may accidentally look at too many rows when we're only trying to return a few are kind of quite varied and get subtle. The cool thing is that there's pretty much one thing that fixes the majority of those problems, and that is indexes. We'll get into their work, but how they work soon, but let's talk about what they actually are. So the majority of the time when you talk about an index in InnoDB, you are talking about a B tree. Sometimes you're going to be using a hash index. They have their uses, but the majority of the time it's the B tree. Now, what do they look like? In code, you'll be familiar with this one. This is what a secondary index looks like. You say index and name the columns that you want to have in it. Now, secondary doesn't mean it's worse than something else, but it does imply the existence of another type of index, which is the primary index. Again, you'll be familiar with this one. You define primary key. Here we defined it on an ID, which is an auto-incrementing integer. These are both constituted by B trees, but they are slightly different how they work, but they both have the same goal, and that is to find data quickly in order. Basically, you want your an index should allow you to very quickly find one row in your database in log n time. And then once you've found that, potentially iterate through a number of records that are adjacent to it in the actual key space. So if we want to quickly look for the value 5, we're going to be able to jump to 5 and then get the value that is at 6, 7, 8, 9, 10. And this has value in enabling just all the basic things that you do in a SQL query. First of all, it allows you very quickly find rows that correspond to the values in your where clauses. It also then allows you to do range queries, which are essentially an extension of that reference query. You can, and then obviously in the same way that reference queries are kind of used for where clauses, you can also use indexes to enable joins to be a lot quicker, which are essentially just a big long list of, I have this value, I want to find it in another table. And last of all, because all the data in indexes is ordered, it allows you to do very, very fast groups and distincts too, both operations that require us to operate on ordered data. So know what they do, we know what they look like in code. What do they really look like? And the answer is really cool. This is a B plus tree. It's essentially like a B tree, which most of you will be familiar with. A B tree is just a way to basically structure a list of a tree of nodes so that we can very quickly get to a specific value. A B plus tree has one extra feature in that the nodes are linked crossways so that you can get to one node and then iterate through adjacent values. It has all the parts you expect, a root node up the top, a bunch of internal nodes to allow us to traverse down to values, and at the very bottom you have key value pairs. Each of these rectangles is a page in MySQL, which is something like 12 or 16 kilobytes, and basically just has a big bunch of values. Very quick to move through pages to get adjacent values. But then when you want to iterate across a page boundary, you'll obviously be doing a fetch from either memory if the page is already cached or from disk. Now we see these values down the bottom, 0A, 1B. What are these in a secondary index? These are actually the pairs of all the things that are in the columns in the index on the sort of top or left there. So eye color blue, last name O'Keefe, first name Shaun or mum or dad, and the dates there, and they map to a primary key. This is an important part of how secondary indexes work. They have the value you're looking up on and then a reference to a primary key. This doesn't sound useful immediately because what do we do with the primary key? We want the actual rows of data. Where do we go from here? And this is getting into why there's that distinction between secondary indexes and primary keys. So the thing about primary keys in InnoDB, they are implemented using a clustered index. This isn't a feature unique to InnoDB, but it's a big important part of how it works. Basically, all of your data is actually stored inside of an index, which is indexed using the primary key. This gives us a number of important properties. It means that if you are doing searches on your primary key, they are very, very quick because all of the data is actually going to be co-located on disk. Whereas your secondary indexes, it'll be very quickly to iterate through the index, but to find the rows that they point to, you'll have to go to the secondary index, find the value you want, get the primary key reference, and then do another lookup, which is most likely going to result in random I/O. So your clustered indexes are your fastest ones to look up on. They are also co-located on disk, so they are quick to iterate through. So what does this look like? We've got our secondary index example there in the middle sort of vertical table. That's pointing to a bunch of primary keys, which are then up the top of the right-hand table, and those are the keys into that second table. And then the second table contains the actual values themselves. So if we want to do a lookup on our secondary index and look up based on eye color and last name, we'll look it up on that, we'll get our corresponding primary key, and then we'll do a search into the clustered index to find the actual rows of data that we're after. But the big take home here is that there isn't like a separate mechanism for storing rows. Your data actually is stored inside of an index in InnoDB. So we know what PKs are, primary keys are now. How do we actually make them? Well, how should we define them? A number of really cool things you can do to make your life easier. First of all, you want small, simple data. Think integers. There's a number of reasons for this. First of all, if they're big, your indexes are going to be bigger. If they're small, they're going to be smaller. A lot of things are also going to reference your primary key. So another table has a foreign key to your primary key. That table will have to duplicate the data that's in your primary key. If it's a big long string, it means you're writing that string twice to different tables. Also, secondary indexes all have to reference your primary key. It'll make your secondary indexes bigger if your primary keys are big. An important thing about simpler data is too, if it's a simple type like an integer, it's easier to compare. Therefore, it's easier to do comparisons across tables, where if it's a string, you have complicated things like collation rules, etc., that are actually going to make it a bit more expensive to do those comparisons, which can really add up when you're talking about thousands of rows. You want to make sure that whatever your primary key is, anything that references it uses the same data type. This sounds really silly, but it can be a big problem. Obviously, if you have to do conversions for operations you're repeating thousands and thousands of times, it can really add up in terms of query time. You generally, and this one kind of runs counter to the idea of having simple data, you may want to put your most used lookups in your primary key. Because it's the fastest one to fetch and iterate through, you may want to leverage it as your fastest lookup. So you may actually want to put string data on there, depending on how it's going to be used. I would say if it's going to be referenced primarily from other tables with joins, use a numeric integer, use a numeric primary key, order incremented primary key. If it's just primarily going to be looked up directly, maybe you can get away with just using the actual direct column values that you want to look up, so strings, whatever. Auto inc is really, really great, and this is mainly to keep your indexes small and your writes inexpensive. If you have an auto incrementing primary key, your pages will get full a lot quicker, and you won't have to split pages as you write data. We'll have a look at why this is the case, but conversely, random insertion order is the worst. So if you have a primary key that's a random number, or which is not something you're generally going to do, but let's say it's a UUID, something that basically completely changes each time you generate a new one rather than increments up by one, you can have some real problems with having massive indexes, not to mention that things like UUIDs are actually quite big and expensive. So let's look at an example why that's the case. So let's say we had 5 values and they all happen to be increasing. So 1, 4, 12, 21, 32. We fill up the first page by the time we get down to 32 and put 32 onto a second page, and then we go back to a random number. So we stop incrementing and get to 16. To insert 16, our first page has already been filled up, and the rules for how they get filled up are a bit complicated, but we don't need to get into them here. But let's say they are full, there's no more room. To make room for 16 in the primary key, remember they're a clustered index, they need to be in order. We actually have to split that first page, squeeze 16 in there and put 21 on a new page. So you can see a number of things happen here. We've got all this wasted space now in those last 2 pages, and 2, we've had to do a bunch of I/O, potentially the stuff that will have to be written to disk to fit in this new value. All right, so we get what indexes are. We understand the relationship between secondary indexes, primary keys, and clustered indexes. How do we actually convince MySQL to use them? And it's not a trivial thing to do. Like, one of the most common things you run up against is you define an index and it doesn't make anything faster. The cool thing is there's pretty much a really simple answer to what you need to do here. MySQL just wants one thing from you, and it is a better access type. If you give it a better access type than a full table scan, it will probably want to use your index. What do we mean by access type? We mean this. Basically, this is a list of improving access types. At the very, very top is the worst one. It's a full table scan. That is essentially where you want to look for something in a table, and you've got no better option than to scan all the values in the table, look at them, and see whether they're what you want. It's very expensive. It will use up a lot of resources, but sometimes it actually is a good option. We'll go into that in a second. From there is a full index scan. This is an index lookup. Is it not an index lookup where you have a reference and you look into an index to find a row? This is actually, you look at every value in the index. This is better than a full table scan because indexes are smaller than the actual table data. They're often fitting into memory. They're a bit quicker than a table scan. We'll use these quite often when we want to search on something, or sometimes when the index includes the actual values that we want to return to the user, which is called a covering index. We'll get into them in a bit too. The main one you're going to be dealing with is the middle one, the index, range, scan, and the lookup. Those are basically where you are doing what you expect with indexes. You're saying, give me a particular value, or give me all the values between these ranges. A same such index lookup on a unique index is a little bit faster, just because it doesn't have to deal with multiple values. And the best outcome is when you can completely factor out the actual select you're doing in the optimizer, just because there's stuff that doesn't need to actually be operated on, but we're not going to hit too many of those. So cool, we have this information. What do we do with it? How can we design our indexes to make them attractive to MySQL and the query optimizer? First of all, try to make sure that one index can service many different query types. This is just a good way to get bang for buck out of all that disk you're using to store your index and the memory. If you look at all your different queries and identify common patterns, common index columns that are queried, put them to the left of your index, and make something that ideally can be used across many different things. It's not so much about making it more attractive as just getting some good value out of that disk space it's using. You want to make sure that for each index you have, that it covers as much of the parameters used in a query as possible. So if your query has 3 conditions in the where, you want to make sure ideally that they're all covered by the index. It's not the end of the world if they're not all covered, but the more things that you cover, the more value that you present to the actual planner, the better. It's also actually valuable, as we mentioned covering indexes before, to have some of the values that you're returning to users quite commonly in the index, as it means you sometimes can do a query and get the results you want entirely from the index without ever going to disk to fetch rows. We'll get into them in a bit. And this is a really important one to remember. You should define an index. The order which you define columns is important because MySQL can, in a single index lookup, can only use the leftmost part of your index. So what do I mean by that? Just say we define an index on eye color, last name, first name, age and join date. You can do a search on eye color. You can do a search with conditions on eye color and last name, but you can't do a search on first name alone. That won't use your index. Similarly, as soon as you put a range query, or sorry, a range condition in your clauses, that's basically where you stop using the actual index. And that's just a virtue of how B trees work. Basically, once you have that range, you've started going across the structure, you can't go back to where you started. So all of these queries here will use the entire index, and you can just see they're just using everything up to the left part of the index. And you can see also, like down in the bottom case, where we have a blob on Mac, that still applies. It will actually use everything up to the last name column and the MC part of that. If we reverse that blob, like we do here in the first query, that will not actually use the last name part of our index. Because the blob is on the left, that is not the leftmost part of the index, we are jumping to the right, and that won't be applied. Similarly, if we have 2 ranges here, the second range won't be able to take advantage of the index. We'll probably be able to get the index to help our query with the age part of that query, but the join date will basically have to do an in-memory sort. Now remember, when we miss that right-hand part of the index, it's not saying that you will not, the MySQL will not use your index to do the query. It's saying it's become a little bit less attractive. That said, there are absolutely cases where MySQL will find an index which kind of does what it wants and then choose not to use it just because it's actually going to be cheaper to just do a scan of the table. And these will be cases where pretty much all of your conditions would pretty much result in you returning most of the table anyway. In those cases, it's just cheaper to pull everything out rather than do all the work of pulling in your indexes, dereferencing the secondary index to the primary key and doing another lookup. So it's not always the case that you can get an index to work. Sometimes it's better not to. Now, we mentioned covering indexes a couple of times. You probably should have a fairly good idea of what these are now. We've mentioned a few times. Basically, the idea is that in addition to the values that you put into your indexes to search on, the things that will be hidden where clauses or joins, you can also add extra values to your covering indexes to commonly referenced columns. So columns that you'll be returning to your user. If your query can actually service itself by only doing conditional lookups and returning a few values that are from the index, you'll never actually have to go to disk if your index is in memory. So this is a really cool little optimization you can make to have bananas fast queries. Okay, so we think we've got the right principles in place. We think we know about how to kind of like, go MySQL into using our indexes we made. How do we ask questions about how it all went? And anyone who's set up Stack Overflow will know the answer to this. It's the explain command. Explain, basically you can bolt this onto the front of any select query that you're running, and increasingly in later versions of MySQL you can also run it on other types of queries, always being careful to make sure that you're not actually adding data to the database at the time. But this basically gives you a breakdown of the decisions that the query optimizer is making in MySQL. So if we look at this particular query here, there's a better version of it, so I've left a slide in there. Here's a better version of it, and if we look at this running, we can run explain on it, and this is the output we get. It is super hard to really get your head around and requires a bit of understanding of a few important things that happen on the back end in MySQL. So let's hit those, and then we'll get into breaking down what this actual result means. So first of all, we're going to talk about the query parser. We've mentioned this before. It basically tokenizes your query and creates a sort of tree, which can be manipulated by the optimizer. The optimizer is the part of MySQL, the server itself, which asks questions of the storage engine about what sort of data it has, like how many rows are in a particular table, what the cardinality of certain columns are, to see whether they're particularly selective, It asks about what indexes it has, and again, get statistics on them. It also applies a few just like common sense things, or like, you know, algorithms that they put together on the server side to say, actually, we can just pretty much factor out this part of a select, or we can take this part of the query tree and move it over here. It also does other great things like the join optimizer. Basically, the order in which you specify your tables is significant, and often by changing the order by which we do the joins, we can make a query a lot faster. So this is what joins here look like. There's an important concept to actually talk about joins here. There's obviously the command in the actual SQL language join. There's also just the concept of an actual lowercase join in SQL. It doesn't really come up that often. If you're just doing regular joins across tables, you won't need to think about it. But if you do start looking at explain and start running things like unions, you'll see that extra rows appear for each union you do or subqueries. This actually means that it's actually showing one record per join. The main thing you really need to know about joins for the basics here is that they represent everything in addition to the first table in the explain statement. So what is join execution here? This is a really important part to understand of how MySQL actually, asks InnoDB for its records. It basically runs through the the joins in a nested loop, same as a bunch of for loops in code. If we have two tables, we'll start on the first row and then we'll step into the second table. We'll do a lookup into that second table based on whatever the joining column is. Let's say it's column 1 here, and we'll find all of the records in table B that match column 1 equals 3. We get 2. We step into the first one. If there is a column C and there's a join, if there's a table C and let's say there's a join on column 2, we'll then say, okay, give us the corresponding matches in table C for column 2 equals 7 here. And then we'll get that result. And once we get all the way down to that join string and we have our first row, we will then return that to the server, who will possibly just send that straight to the client. And then we walk back up to table B. There we go. Are there more matching records in table C? If not, walk back up to table A. Are there more matching records in table B? Yes. We're now down to column 1 equals 3, column 2 equals 1, the second row. And we'll walk down there and then we step back up. And the important thing for understanding this model is that it's basically how you should think about how it's using the indexes. It's using an index for each of these steps across the tables. Now, after we've gone through those nested loops, again, as each sort of walk into that tree, or the bottom of that loop returns, we'll return a row back to the server. The server may do some amount of post-processing on it. If it couldn't actually get, for example, if your query has an order by in it, or a group by, or asks for unique values, and it couldn't actually get that result from the index, it'll manually do it. Sorry, not manually, it'll do it itself in memory before returning back. But in the case where you actually completely just work off indexes and rows in InnoDB without any post-processing, you can directly return those rows to the client, which is a great outcome in terms of performance. So let's go back to our actual query here. We've got 3 tables: film, film actor, and actor. Remember in that order: film, film actor, and actor. We're going to run explain on it and we get this result. Let's break down each of these rows, talk about the columns and see what's happening. Now, the first interesting thing you'll see is it's actually started with the actor table. You can see where it says table actor. This is interesting. So that's the join optimizer at work. It's saying, actually, I want to use the actor table first. And the reason it's done that is that probably it's actually a far smaller table. It's figured that out from statistics, and it's actually going to just do a full select on that entire table and then iterate through the nested loops on it. So that means you'll have to do fewer iterations overall. You'll do the first row, and let's say there's up to 200 rows, which we can see here, 200 rows in the rows for the rows value. It'll have to do that 200 times and then do very quick lookups into the larger tables, which is far more desirable than going through, let's say, a 10,000 row table and doing a bunch of lookups into smaller tables, because you aren't getting that performance advantage by using an index to look into smaller tables. log n is log n no matter where you go. So let's go through the actual rows here so we can understand it better. ID is not super useful here for most cases, nor is select type. ID is the identifier of the select that you're doing. So if you're just doing a select with a bunch of joins, this will always be 1 for each row in explain. It's only when you start doing subqueries with other selects in them that you start getting ID1, ID2, and so forth. Likewise, if you're not using subqueries and unions, your select type is always going to be simple. Again, we're not going to get into our subqueries and unions here. They're a bit of a hard mode version of this. It gives you the table that this particular row is on. Again, we're working on actor first, and the select type is all. It's basically saying, do a table scan, give me everything. Possible keys is interesting. It is telling you the keys that MySQL has deemed could be valuable for performance to make lookups quicker. And it's found primary key, but it's decided to actually not use any key at all, which is specified by key null. Now, often you'll have cases where it says maybe lists 3 possible keys and uses a completely different key, which sounds unintuitive, but what you have to understand is possible keys is saying, I think these keys can make the lookups faster. But you got to remember covering indexes. What it may end up decide to do is actually use a covering index instead of actually taking advantage of an index for lookups. And a covering index isn't necessarily an index that's going to make lookups quicker. It's just going to reduce the amount of data we need to look at. So the resulting key can not be included in the set of possible keys. Key length, null here, but remember we talked before about possibly only using a leftmost subsection of an index. This will tell you whether that's actually happening. Key length is not the number of columns you're using from an index, it's the number of bytes you're using. So for example, if you have a 32-bit integer as the first part of your index and then a 6-character string, and you're told that you're using that the key length is 4, that means that for whatever reason MySQL has decided to only use the integer part of your index and isn't using the string part. Ref type isn't super interesting here. Rows isn't interesting either. We'll get into it soon. Extra is a really cool row, but there's better examples of it in the next one. Here again, the ID is 1. It's a simple select because again, we're just inside a join. We're now looking at the film actor table. The type here is reference, which is a bit different to before. That means we're actually doing an index lookup instead of an actual full table scan. So we're actually saying, given a specific value, look up for a particular record in this table. We've chosen a number of possible keys which could make things faster, and we've decided the primary key is going to be the fastest lookup. We're using a key length 2, which means we're using the first 2 bytes of that index to do the lookup into this table. And the value that we're correlating between the previous table and this table is given to us in the ref row, which is the actor ID column in the actor table. Rows here is now interesting. It's saying 1, which doesn't mean there's only 1 row in this table. It means that each time we do a lookup from a value in actor, from actor ID, into this table, we will on average have to inspect 1 row. So that means for all the values in actor, when we reference those into this table, into film actor, we'll probably only have to look at 1 row to get a result. Last of all, extra is really interesting. So extra is generally the row that gives you information about what's happening in MySQL, not in InnoDB. And it often says something that doesn't sound like what it is. So here it's saying using index. That's not telling you that it's using an index for the lookup. It's actually telling you that MySQL has decided to use the index as a covering index to get its values back. And there's a whole bunch of things like that that give you information about the decisions MySQL's made in extra. For example, using file sort is common. It means that it's had to do a sort in memory in the server after it's gotten its results back. Also using temp table, which is that it's having to use a temporary in-memory table to do some of that sorting. And this guy's very similar. The only interesting thing to kind of point out here is that it's using an equal ref, so that means that it's able to use a unique key rather than a regular secondary index here without a unique constraint. And that's how we work. We basically iterate through those 3 tables. Again, doing that nested loop. Each time we go across, we use the key that's shown here in key to do the lookup based on the value that's in the previous table shown in ref, using the reference type shown in type. And a last little tidbit, if you want to actually look at how the plan breaks out in a tree, explain with extended show warnings. This is a really cool thing. It actually gives you a little tree to show how everything's been planned out. But that's pretty much it. Thank you very much. I was Shaun O'Keefe, again from Style Education. Hit me up on YoMilk if you have any further questions. And yeah, thank you very much.